So today we are going to go through a whirlwind crash course, if you'll forgive the term, into space medicine, what exactly it is. You've heard a little bit about me. My name is Dr. Shawna Pandya. I have a whole host of titles, some of which you'll get to see during this presentation when we talk about how we prepare for space. And here's just a few more of my affiliations. By the end of this compressed course into space medicine, I hope you'll have a sense of some of my work, what the challenges of the spaceflight environment are, how we design for space, emerging technologies that can help us prepare for the space medicine environment, as well as emerging challenges in space medicine. So let's get to it. Before we begin, let's start with a question. Imagine you're going to the moon today and you are the crew physician. Knowing this, what will you bring with you? In order to know what you're going to pack for the moon, you have to know what the hazards of the moon and the spaceflight environment are. And this includes a whole laundry list of everything from increased radiation to the acceleration, deceleration loads of launch to altered day-night cycles. So that if you're on the International Space Station, that is 16 sunset cycles per 24 hours, one sunset, one sunrise every 90 minutes. You have to deal with the psychological demands of an operational schedule that is scheduled down to the 5-minute mark. You have to be able to play nice with your crewmates in a confined space because nobody wants to be the astronaut that is voted off the spaceship. That just makes it awkward for everyone involved. And then there's, of course, the off-gassing from organic compounds that can clutter up the atmosphere and the environment. We have to trust the life support systems engineering to keep our atmosphere habitable, comfortable temperature, with a comfortable pressure to scrub the atmosphere of any volatile organic gases, as well as trust that we'll also run into the same lumps and bumps and everyday trauma, abrasions, and sicknesses we might run into on Earth. And then, of course, there's the big thing that we haven't talked about yet, the thing that we all talk about and think about when we talk about space, and that, of course, is microgravity. So suffice to say that every single bodily system is affected by the space flight environment. Whether we're talking about our bones, which lose density at a rate of 1.5% per month without countermeasures, reflecting an osteoporotic space condition on Earth, our muscles will lose mass, the fluid in our legs shifts upwards, causing puffiness of the face. We feel congested as if we have a cold, so food has to be more flavorful. Even the cerebrospinal fluid, that proteinaceous brain and spine juice that bathes our brains and spines, shifts upwards and doesn't drain as well during spaceflight. And so this last finding about CSF is called the Spaceflight Associated Neuroocular Syndrome, and it's a relatively recent finding over the past 15 years or so. And the bottom line is, despite 60 years of human spaceflight, the surprises of what we know about how humans adapt to the spaceflight environment keep coming. So just as recently as 2019, routine handheld ultrasound experiments of the jugular vein found, lo and behold, there was a blood clot in the necks of one of the astronauts. So then we had to ask, well, does being in space lend itself to a condition that relates to more blood clots? We know that there's gender differences, so that spaceflight neuroocular syndrome, the SANS that we talked about, tends to affect men more disproportionately, while women are more prone to bladder infections due to their anatomy. We know that women are more prone to orthostatic hypotension or fainting post-landing, while men are more prone to cardiovascular changes once they get to space. So all of this is simply to say, if you know nothing else and you remember nothing else about space medicine after this presentation, if someone on the street stops you and asks you what you learned, it's simply that space is trying to kill you. And that's what we just know from lessons of decades in low Earth orbit. And beyond that, it's not just space, it's the Canadian astronauts that are trying to kill you as well. This is a very real headline from about a year ago in the Calgary Herald saying that Canadian astronauts were once free to rob and kill with abandon in space because there was a loophole in Canadian law that protected astronauts from being prosecuted should that happen. Americans, rest assured, we have since closed that loophole. We're safe again. So, coming back to the challenges of spaceflight, this is what we know from decades of being in low Earth orbit. But we have to ask the question, what happens when we go beyond low Earth orbit? And that's a very practical question because it's not simply that, well, a theoretical question. NASA, the International Space Agencies, its partners, as well as the commercial sector have very real plans to go beyond LEO, starting with the moon and beyond. So as early as the later part of this decade, the Lunar Gateway will be established. This is humanity's first deep space station in orbit around the moon. It won't be as big as the International Space Station, and it won't have as long duration missions, but it will have a view towards establishing lunar science, Earth observation science, sun science, and also serving as a waypoint for landings to the moon, which paves the way for the Artemis missions, which is NASA and the international community's plan to put the first woman of color first woman, next man, the first person of color, and the next man on the moon's surface, and paving the way towards establishing permanent surface operations on the moon by the end of this decade. So it's safe to say we need to start thinking about what happens when we go beyond low Earth orbit. The other point of the Artemis missions is to serve as a test bed for Mars and test what we know about space medicine and human safety. So what we know about long-distance, long-duration missions in deep space is kind of limited to what we've learned about the Apollo missions. And even those brought home a treasure trove of biomedical data. We know that there's hundreds, if not thousands of pages related to ergonomic issues that came with EVA suits, extravehicular activity spacesuits during moonwalks. We know that lunar dust compounded astronauts' movement. It served as a very potent skin and eye and respiratory irritant. So for anyone who tells you that the moon landing was fake, they put a lot of effort into it. And this is a really good overview from Nature that just came out in the past few months about what we do know about lunar dust so far and what we still need to figure out, because we just know that what lunar dust from a few landing sites looks like. If we're serious about going to the lunar South Pole, well, can we make the assumption that that lunar dust is the same as the lunar dust we've studied so far? We haven't yet talked about radiation, but the bottom line is that the higher up we go, the more radiation we have to contend with. So at the level of commercial spaceflight, we're exposed to, commercial air travel, we're exposed to about 40 times the amount of radiation we would standing here on the Earth's surface. When we go to the level of the ISS, we're exposed to about 250 times the amount of radiation as we would in one day on Earth. So close to a year's worth of radiation exposure in one day. By the time we go on a deep space mission, that is approximately 700-fold the equivalent of space-based radiation that you would gain exposure to. So that's the equivalent of about a full body CAT scan every 5 to 6 days. Plus, the higher up you go, the higher energy radiation you have to contend with. So at least at the level of the International Space Station, you're still relatively protected within the confines of the Van Allen belts. That pesky, high energy ionizing radiation that comes from solar particle events, from galactic cosmic radiations, is still relatively filtered out. By the time you get to the moon, you don't have that protection. For those of you who are Douglas Adams and Hitchhiker's Guide to the Galaxy fans, you may also know the problem of space being big. Space is so vastly, hugely, mind-bogglingly big you wouldn't believe it, and that also applies to telecommunications traveling at the speed of light. So the further out we go, the more of a time delay there is between round-trip communications. At the level of the moon, that's only about 2.4 seconds round-trip, so a little bit annoying to have a conversation, but definitely doable. By the time you get to the red planet, depending on the alignment of Mars and the moon, Mars and Earth, that's about 6 to 46 minutes round trip delay in communications. So now, coming back to that original question we asked, if you're the doctor on a mission to Mars and you have a cataclysmic event, like a cardiac arrest, you don't have time to radio back Earth for help. So, coming back to that question, knowing that there's a huge laundry list of everything that we talked about with respect to radiation, time delay, dust exposure, skills deterioration, how do we talk about this framework of how we think about deep space health challenges? So we call this the RIDGE framework. Stands for radiation, isolation and confinement, distance from Earth, altered gravity, and everything else, which includes hostile environments, altered day-night cycles. So we talked about 16 sunrise-sunset cycles on the ISS at the level of the moon's equator. That's 14 days of day, 14 days of night. We talked about lunar dust. So, have I stressed you out adequately yet? You're the crew physician. What do you do now? So we talked about the problem space. Let's start talking about the solutions that we have at our disposal to help keep our astronauts healthy, productive, and operational in space. The first, of course, starts with selection. If we can prevent a problem before it even starts, then we're actually setting ourselves up for success. So anyone out there who's familiar with space agency selections know that we're selecting for the healthiest of the healthy, physiologically, physically, and psychologically. So reasons that people have been screened out of selections in prior years from NASA and Canadian Space Agency selections include iron deficiency, being colorblind, having thyroid issues, being diabetic. Basically, if you have any type of medical issue, you're at risk of being screened out, and that's to be able to keep you healthy on mission. So it starts with prevention. It continues with rigorous pre-flight, in-flight, and post-flight rehab. It also continues with biomonitoring, countermeasures during the mission. So astronauts famously have to perform 2 hours of resistive exercise and aerobic activity 6 days a week on the International Space Station. It also continues with nutrition. Despite the constraints of the spaceflight environment, nutrition, but remember, we talked about astronauts having increased congestion. They don't have much of a sense of taste. It has to be flavorful, nutritious, textured, have a long shelf life. So there's all these challenges to contend with. At the same time, the crew medical officer, the CMO, there's no physician continuously crewing the ISS. You have a CMO who's been trained for about 40 to 60 hours of basic medical training. Other tools we have at our disposal include computer modeling techniques. So this is a snapshot of the IMM, the Integrated Medical Model, from NASA's Johnson Space Center Exploration Medical Capability. And basically, it allows us to extrapolate what kind of medical supplies and what volume we'll need based on what is on the ISS, based on how many people are going on our mission, for what duration, what level of risk of loss of crew life and loss of mission that we're willing to accept. And if you're looking at this, you're saying, well, hey, Shawna, that's actually pretty one-dimensional, because what if I use the same antibiotic for a bladder infection, for a respiratory infection, and then a skin infection? I've depleted my supplies. I'm glad you asked. So this has also been supplemented with a new medical model based on neural networks and Bayesian modeling called the Medical Extensible Dynamic Probability Risk Assessment Tool. Try saying that 3 times fast. We call it the MedPrat for short because it's a lot easier to say, and it allows us to account for multiple adverse events, countermeasures, repairs at different time points in the mission so that we're able to generate a series of different possible outcomes. The other part of knowing how to prepare for space, in addition to knowing our tools as well as what hazards we're preparing for, include knowing what has happened in spaceflight previously. So this is a snapshot of the XMC's top 100 medical conditions, which includes everything from the terrifying cardiac arrest in space to mass trauma and mass hemorrhage to the more common, everyday, not life-threatening but annoying congestion headaches, CO2 headaches, to the terrifying but not life-threatening diarrhea in space. We also need to look at what has happened previously in spaceflight by history. And luckily, as you can see, it tends not to be the things that will kill you, but the things that are more annoying. So skin infections, respiratory infections. You'll see that cardiac arrhythmias have happened, but when they happen in spaceflight, very luckily, they tend to be self-limiting and asymptomatic. So the astronauts don't know what's happening. It goes away on its own. So how do we pack for space, knowing what we have to contend with? Those of you who are hikers and campers, you know this concept is called the backpacking concept. You can't bring it all with you. Everything you bring with you comes at the expense of something else. So if you're limited by mass and you're limited by volume. I like to call this the Aladdin principle of packing for space because it's phenomenal cosmic power to get to space, itty bitty living space once you get there. So in summary, when we're thinking about how we pack for medical missions on this long-duration spaceflight, things we have to bring have to be low cost, low volume, easy to use, low power, long shelf life, and low astronaut time intensity to use. In summary, if you remember nothing from this part of the talk, space is hard, space is expensive, and space, again, is trying to kill us. So knowing this, it makes sense that we want to prepare ourselves as much as possible in space-like environments before we ever head up to space. So how do we do that? Well, here's a question. What does the ISS have in common with a remote village in Kenya or an Arctic medical deployment or an underwater research habitat? And the answer is they're all examples of remote, resource-limited, isolated, and confined environments. And so you might say that they're analogous in some way to the spaceflight environment, which is why we call them analog environments. And so we can actually prepare ourselves for space by learning, training, and working in analog environments. And I want to take you through some of my work in analog environments in this next part of the talk. So let's start with altered gravity environments. So far we've talked about zero-G, but sometimes we need to talk about hypergravity when we talk about the increased acceleration loads of launch and landing, as well as altered gravity when we talk about 1/6 gravity on the moon and 38% gravity on Mars. And so some of you may be familiar with the concept of the vomit comet or parabolic flight. It's just like when you're in a roller coaster and you're cresting over the top of that roller coaster, your heart lifts into your stomach for a second and you're weightless. Or just when you're going down an elevator, again, your heart lifts into your throat for a second. So you're doing this on a flight and your flight is climbing up at 2Gs and then you're leveling out, falling at the same rate of the plane. And that gives you 20 seconds of zero gravity to play around with to be able to perform science, increase technology readiness levels, make something space ready. So we've done that with spacesuits, intervehicular activity spacesuits, to test the range of motion and test how they act under pressurization with the visor down in the zero-G environment. We've, as you can tell, 20 seconds is good, but it's not a lot to play around with when you're trying to test technology in altered gravity environments. So gravity offset is another way of doing that. This is work that we've done with the Canadian Space Agency, testing a different type of spacesuit called an EVA, or extravehicular activity spacesuit. And basically gravity offset allows you to float a certain percentage of your weight, whether it's 99% to replicate microgravity or 83% to replicate lunar gravity. And basically you can start to perform work in altered gravity environments, again, to test the capabilities of the suit. We learn a lot by working and living under, on, and in the water. So this is an example of a neutral buoyancy lab. This is some work we've done through the International Institute for Astronautical Sciences. And again, this grants us a longer period of neutral buoyancy to simulate weightlessness to perform meaningful work. Here we're practicing doing a spacewalk out of an airlock to be able to replace a module outside of a strut in an ISS simulation. We learn about crew dynamics and science in isolated and confined environments. This is a Neptune aquanaut mission where I gained my aquanaut designation in 2019. This is at the Jules Undersea Lodge in the Florida Keys. And like everything else in this presentation, Neptune is an acronym. It stands for Nautical Experiments in Physiology, Technology, and Underwater Exploration. There will be a quiz on that later. 13 miles horizontally from the Jules Undersea Lodge is the Aquarius Reef Base, where NASA sends its astronauts for the same reasons, to gain those crew dynamics and focus on science technology demonstrations. The NASA calls its missions NEMO at the Aquarius Reef Base, so that stands for NASA Extreme Environment Mission Operations. And the coolest part about being in this habitat is you're in this little school bus-sized habitat, and all these fish are swimming by, and all of a sudden you're wondering who's in the aquarium looking at who. You also learn by simulating and working above the water. So through our work at IIAS, we have run off-nominal Orion capsule landings. So off-nominal landing is a fancy way of saying crash landing. And basically we want to say in emergency egress operations, how are we able to egress in our IVA suit? And how does the suit interface with the water in the emergency raft? I've learned the hard way. It's really important not to get water in the suit. We also learn by living and working in Mars and Moon-like environments. So this is from our planetary geology course, where we've taken lessons learned from Apollo missions and redesigned geologic tools for EVA on the Moon. I've also run missions as the crew medical officer and as the commander at the Mars Desert Research Station in the Utah Desert. So it looks like Tatooine, but it's actually just outside of Hanksville in the US. And really, you're living and working as if you were on Mars. So if you're suiting up, you're going outside. If you're going outside, you're suiting up, because if you didn't, the Martian environment would kill you. And it's a great test bed for being able to practice and test medical simulations and operations in an isolated and confined environment, like we're doing here on one of our missions. And we don't even need to take ourselves out into the middle of nowhere to be able to practice in isolated, confined environments. We can simply take away resources. We can take away the creature comforts that we normally have. So this is a lesson in crew resource management from one of our high altitude noctilucent cloud campaigns. Basically, we're working as a crew of 3 at 19,000 feet in an unpressurized research aircraft. I'm the payload specialist, and we're testing a brand new type of instrument over my right shoulder there to be able to get more information about the three-dimensional structure of a noctilucent cloud thought to be related to climate change. We don't even need to go into the middle of nowhere to learn about crew resource management. So this is a snapshot from my space medicine course where we basically take medical layfolk with no medical training or background and turn them into a space medical MacGyver by putting them in the Colorado wilderness and teaching them principles of triage, treatment, and assessment, building on principles of wilderness medicine and bringing in elements of the space medicine environment. So, we've talked about how we prepare for space in the context of knowing the hazards of space, but let's take it back to the big picture. What are we trying to do here? We're trying to keep astronauts healthy in space. We're trying to keep them not just surviving, but thriving by also meeting the standard of care as we would on Earth. And the gold standard, if we were to send a crew on Mars, the simplest thing if we took away all constraints would be simply to bring another Earth with us. What if we took away constraints and simply terraformed Mars, assuming that technological ability was not an issue? We could bring the gravity, we could bring the magnetosphere with us, we could bring an atmosphere with us, and suddenly we wouldn't have to worry about all the challenges we've been talking about this presentation. So that's a little bit futuristic, but maybe we can learn about not just meeting the standard of care on Mars when it comes to healthcare, but surpassing it. And we do that by borrowing on ideas from science fiction. So in the last few minutes here, I'd like to talk about what comes next and what is on the horizon of space medicine when we're talking about the future of space medicine on the moon, Mars, and beyond. So we know that there's certain topics that we previously haven't talked about. We're thinking more and more about psychological resilience and how that comes into play for a longer duration mission on Mars when we suddenly our crew profiles, our mission profiles span 3 to 5 years. And we also haven't talked about sexuality and reproduction in space, which, if we're serious about becoming an off-world multiplanetary species, well, that implies procreation. So some of my work in book chapters have focused on those two regions, areas. And some of my other work has focused on commercial space flight. So when we democratize access to space, that means anyone can go. That means people with diabetes, people who've been colorblind, people who would have been typically disqualified from a NASA selection can go. So some of my work has focused on medical guidelines for suborbital commercial space flight. If we're serious about having long-duration off-world missions, we need to think about how we're going to build up permanent off-world medical capabilities, in what stepwise fashion we're going to do that, how we're going to train the personnel to do that, what kind of technologies come with it, and what analogs we can borrow off of from previous lessons learned, whether we're talking about military deployments on Earth, refugee camps on Earth, or lessons learned from the ISS. We also need to think about how our medical capabilities are going to change, knowing that the type of work that we do on long-duration missions are going to change. EVAs, surface EVAs, imply a certain amount of risk in rocky terrain, slippery terrain with dust exposure. So our medical capabilities need to evolve as well. And the European Space Agency is actually focusing on that. So this is their Lunar Evacuation System Assembly. It's called LISA, and it's a concept that was tested on a NEMO mission for rescuing a downed astronaut in the field. And of course, in the area of COVID-19, we can't get away without asking, what happens when we have the first moondemic? What happens when COVID comes to the moon? If we're suddenly in 1/6 gravity in a COVID pandemic on the moon, do we need to go from socially distancing from 6 feet to 36 feet? These are questions that we need to start thinking about. And NASA's kind of already thinking about it. This is a snapshot from their medical concept of operations for Mars. This is from 2019, and interesting to note that there's plans for evacuation if something goes wrong on Earth in peri-Earth orbit, but the second you go into a trans-Mars injection orbit, there is no plan for evacuation. So my advice currently is, knowing this, don't send your favorite astronauts, or perhaps start thinking of plans for medical evacuation or contingencies when it comes to medical trauma on Mars. Believe it or not, there's groups working on CPR in space. This is a snapshot of the guidelines from the European Society for Aerospace Medicine. So if there's a concept in Mars, a concept in space medicine, someone's working on it. What about if you get appendicitis on Mars? Do you want to have to do an appendectomy on Mars? There are certain physicians who say, no, just remove your appendix of your astronauts before they ever get to Mars. And that sounds like it's a little bit far out there, but there's precedent on Earth. So for those of you who have a bit of a aversion to gory photos, you may want to look away. But this is a snapshot of Leonid Rogozov. He was a Soviet physician in 1961 on a polar deployment. He felt some right lower quadrant pain, tried to walk it off. Then he sprung a fever. He took antibiotics. He still had a fever. And then he realized, I have appendicitis. I'm the only doctor here. I'm the only one who can take it out. So there, he fixed it. He did his own appendectomy. Now imagine having to do that on Mars. You do not want to. So that's why certain flight surgeons are proposing doing appendectomies on astronauts before they ever leave for the red planet. And believe it or not, there's precedent for that on Earth. This is a picture of King George Island, where Villa Las Estrellas, a Chilean settlement off of Antarctica is. And the rule is for anyone 6 and older to live there because they're so far from definitive medical care. They need to have an appendectomy if they're allowed to live there. We need to start thinking about food for space and how we're going to bring food with a shelf life of 3 to 5 years to be able to survive the duration of a Martian mission. This is a snapshot from one of the companies I advise called Astreas. We also need to think about solving the gravity problem. So again, borrowing from ideas from science fiction. We first saw it in Space Odyssey 2001 and multiple science fiction stories. Why not use simple physics? Acceleration squared over radius gives us partial gravity. And so one of the companies I advise, Orbital Assembly, is actually working on this, building the world's first partial gravity, artificial gravity rotating space station. Some of you might be saying, well, why not just get to Mars faster? Can't you build a faster engine? Someone is also working on that. That's as a concept for the Vasimir plasma engine, getting to Mars in 39 days rather than in 6 to 9 months. And then some people say, well, that's boring. What would you do? Why not just hibernate? The European Space Agency has run a study on the concept of having humans hibernate and awakening them 3 weeks before they get to the surface of the red planet. And they figured out you can save on 33% of your spacecraft volume by doing that. So the bottom line is there is a lot to consider when we think about long-duration spaceflight. We can talk about human enhancement, engineering the perfect astronaut. This is a study from 2017 in which the researchers proposed splicing elephant genes into humans, not to create some sort of elephant-human hybrid astronaut, but because elephants don't get cancer. And the reason is they have so many copies of cancer-editing genes. The idea is you splice those genes into a human to protect astronauts when you're willingly and knowingly sending them into a high radiation environment. There's precedent for this. The Rodent Research 19 experiment from the International Space Station came back in September 2020. These are genetically engineered mice. You can see the muscular, genetically jacked up little mouse on the right there. Was prone to less bone density and muscle mass loss compared to the non-mutant mice. So NASA is literally engineering Mighty Mouse. The bottom line is there's no shortage of problems to solve. And so when we talk about preparing for long-duration human spaceflight, we're going to have to science the space out of this with a little bit of space MacGyvering as well. So given that, we need all disciplines, all comers. So if there's anyone out there with a passion for solving difficult problems, we need you, whether you're a biologist, scientist, inventor, engineer, researcher, or simply the curious. And it all starts by solving things one step at a time. So thank you very much for your attention. I look forward to your questions, and let's get to it.